In this video, we're going to talk about expanded octets and their relationship to Lewis structures. To understand expanded octets, we have to go back a little bit and think about the material that we learned in Chapter 7 when we first learned about atomic orbitals. And if you remember in that chapter, depending on the quantum number n, there are certain allowed values of L. Remember that L can be anything between 0 and n minus 1. So when the principal quantum number n is equal to 1, L can only be equal to 0. And those corresponded to s orbitals. And so when we look at hydrogen and helium that are in the first row of the periodic table, those orbitals that are filling have a principal quantum number of 1, and so only s orbitals are possible. In the second row of the periodic table, n is equal to 2, and in that case, L can be equal to 0 or 1. When L is equal to 0, again, those are s orbitals, and when L is equal to 1, those are p orbitals. When we get to the third row of the periodic table, n is equal to 3, and L can be equal to 0, or 1, or 2. And when L is equal to 2, that corresponded to the d orbitals. So elements that are in the third row of the periodic table and below have d orbitals that can be involved in chemical bonding. If I just have the s's and the p's, that's where the octet rule comes from, right? I can put 6 electrons in a p orbital, 2 electrons in an s orbital, that adds up to 8. If I have d orbitals possible, I can have more electrons around that central atom in a Lewis structure. And so when I have elements that are in the third row of the periodic table and below, we want to look out for the possibility of expanded octets. And the first example that we're going to do is Xenon Tetrafluoride. So xenon is the least electronegative element among those. So xenon is my central atom. The fluorines will be arranged around it as terminal atoms. And when I count up my electrons, I've got 4 fluorines, each with 7 valence electrons, and the xenon has 8 valence electrons. So when I add those guys up, I get 36 electrons to use. So I have my 2, 4, 6, 8. Now my lone pairs. That's 14. That's 20. That's 26. And that's 32. And I still have 4 electrons that I need to distribute. My terminal atoms are full. And if I look at the xenon, it's got 2, 4, 6, 8 electrons around it already. So if this was a first or second row element, I'd be stuck. But because xenon is well below the third row of the periodic table, it's got empty d orbitals that can be involved in chemical bonding. And so anytime you've given all of the terminal atoms their octet of electrons, the extra electrons go on the central atom. And because xenon is in the third row or below, it can accept more than 8 electrons. And so those last 4 electrons will go in as lone pairs on the xenon atom. And so that is the Lewis structure for xenon tetrafluoride. And I can only put more than 8 electrons around the central atom if it's in the third row of the periodic table. And when that happens, we say that xenon has an expanded octet. Let's do another example on the next slide. Okay, this time we're going to draw the Lewis structure for the sulfate ion. And sulfur, if you look at the periodic table, you can see is in the third row. So we have a possibility of an expanded octet in that case. To remind you, the sulfate ion is SO42 minus. So sulfur will be my central atom. When I count up my electrons, I've got 4 oxygens. Sulfur also has 6 valence electrons, and because it's -2, I've got 2 extra electrons. I have a total of 32 electrons to distribute. So I start with my single bonds, 2, 4, 6, 8. Now my lone pairs. It's 14. 20. 26. 32. So I've distributed all my electrons, and when I check, everything has a complete octet. So at this point, we might say, hey, complete octets, distributed all my electrons, my Lewis structure is done. But because sulfur is in the third row of the periodic table, it's actually possible to expand the octet on it. And so if I wanted to, I could take one of the lone pairs on one of the oxygen atoms and make that a double bond. I'm actually going to do that. That may not make much sense at the moment, but I think in a second you'll see why I want to do that. So I'm going to draw another resonance structure. This will be another valid Lewis structure, so it's an example of a resonance structure. All right, because sulfur is allowed to have an expanded octet, it's okay that it has 10 electrons around it. And so you might ask yourself, that's fine, we can draw that, but why would we want to do that? Why not just stick with the first Lewis structure that we had? And to explain that, let's look at the formal charges on the atoms in these two Lewis structures. So the oxygen atom here has, I count half of the bond electrons, so it gets 1, gets all its lone pairs, so 2, 3, 4, 5, 6, 7. Oxygen normally has, when it's in a neutral atom, has 6 valence electrons, so these single bonded oxygens have a -1 formal charge. They're all -1, -1. This double bonded, or I'm sorry, still just single bonded oxygen, so they're all -1. When I look at sulfur, it has 1, 2, 3, 4. Sulfur normally has 6 valence electrons, so that sulfur ends up with a +2 formal charge. All right, now let's check the formal charges in the Lewis structure that I've written below. So the single bonded oxygens aren't going to change, they'll all be -1 still. But now when I check that double bonded oxygen, I count 1, 2, 3, 4, 5, 6. Oxygen, when it's a neutral atom, has 6 valence electrons, so the formal charge on that double bonded oxygen is actually 0. And now when I check the sulfur, it has 1, 2, 3, 4, 5. So now its formal charge is down to +1. And so remember, when we talked about formal charges, that the best Lewis structures are the ones that have the smallest magnitude of formal charges. So by expanding the octet around sulfur, I was able to reduce the magnitude of the formal charges. And so this Lewis structure that I've written on the bottom is actually a better Lewis structure for the sulfate ion. And I was able to get the magnitude of the formal charges down a little bit. If I make another double bond, I'll be able to get them down even more. And so another Lewis structure that we could draw would be the following. All right, and now if I sign my formal charges, the single bonded oxygens are still going to be -1. My double bonded oxygens are going to have a formal charge of 0. And now when I look at the sulfur, 1, 2, 3, 4, 5, 6. And so now the formal charge on the sulfur is also 0. And so this is in fact the best resonance structure for the sulfate ion because it minimizes the formal charges. Now you might say, well, why don't I go ahead and make more double bonds? Well, remember that the formal charges have to add up to be the total charge of the species. And so because this is a -2 ion, I'm always going to have at least a -2 total of formal charges. And so if I go on and make more double bonds, it's actually going to make the sulfur negative. And of course, it makes more sense to have the negative charges on the more electronegative oxygen atom. And of course, I could draw a number of equivalent resonance structures for this Lewis structure. But this particular one is representative of all of the best resonance structures for the sulfate ion.